So this is the workshop which is organized by the Center for Machine Learning, Faculty of Physics, University of Warsaw, as well as the National Competence Center in High Performance Computing, represented by Interdisciplinary Center for Mathematical and Computational Modeling, also University of Warsaw. And the topic is physics-informed neural networks. Let me come to the next slide. We'll be talking about physics-informed neural networks, which abbreviation is PIN or PINs. Question is, what are PINs? PINs lie at the intersection of traditional physics, model creation, and purely data-driven neural network approach. They use data-driven supervised neural networks to learn the model, but also use physics equations that are given to the model to encourage consistency with the known physics of a system. And regarding topics, we'll be talking about, we'll provide you a kind of an introduction to the concept of PINs, mathematical foundations, as well as applications of PINs in science and engineering. Regarding objectives, objectives are related to say, understanding the basics of PINs and neural operations, training PINs to solve research and engineering problems, as well as train neural operators to solve a variety of machine learning tasks. Now, when preparing this workshop, I was thinking of giving a kind of a introduction to the nature of PINs. And I thought that maybe a kind of an intuitive approach would be the best option. So I assume that all of you, or at least some of you, have already some experience in machine learning and neural networks. And the question is how, say, physics contributes to the development of this methodology. So let's analyze the PIN methodology using, say, mathematical equations. And for example, consider a partial differential equation, which has the form as you see here. It could be any partial differential equation. We can think, of course, an example. I have chosen an example based on the heat transfer. This is the equations. It's a linear model. And we can define the physics loss function. And it's derived from this equation itself. PDE stands for partial differential equation. So let's consider a simple example like this. And we can actually take the square of this equation. And in this way, we can define the physics loss function. Typically, when applying, when using machine learning methods, typically one defines that so-called data loss function based on data. So we have this definition below. The data loss compares the predicted solution with the available observational data. So a typical application of neural networks is based on this data loss function. Here we are adding additional term, physics loss function. So the total combined loss is the sum of these two elements. And this combined loss is minimized during training. And the neural network parameters are set up through optimization to minimize this loss. After this, the training is applied, and the training process involves inputting spatial and temporal coordinates along with any available observational data into the pin and adjusting the neural network weights to minimize the combined loss. And after the network is trained, the pin can predict the solution. So in this way, we can account for physical equations, for physical rules. Of course, other constraints are also possible, can be incorporated in this framework. Regarding lectures, today, Dr. Szymon Nowakowski from Center for Machine Learning will give you an introduction to PyTorch, which is a kind of environment on which applications are built up. And then there will be some hands-on exercises, writing and running Python in Colab, using PyTorch to create and train simple neural networks. In a week, Dr. Marek Bukowicki, also from our center, will give a more detailed introduction to pins. So this will refer to what I was talking, what I was describing you. And also more details about physics-informed loss functions. And then, of course, exercises. And at the end, Dr. Grzegorz Gruszczyński from ICM also will be continuing exercising, training a pin for parameter identification in a selected partial differential equation. Well, the question is if the physics-informed neural networks is a kind of a important field, or maybe not so important field. It appears to be very important. Actually, the number of publications which develop or apply pins in various fields of physics and other natural sciences, grows really very quickly. I just checked what's appearing in literature in different areas of physics, and for example, in nuclear physics, you have a paper on pin based on domain similarity for prediction of nuclear reactor transients. It was published at the end of 23. Nuclear magnetic resonance and medicine, you see another paper. Electronics. I will not be reading the titles of these publications. These are just simply examples. If somebody is interested, of course, you can have a look and learn what is being developed in electronics, in molecular biophysics and bioinformatics, in general in multi-scale modeling. Also in scientific computing and interdisciplinary studies, in fluid mechanics, in physiology, astrophysics and plasma physics, also in space sciences. Okay, so you see, that's really very quickly developing area. And I would like to finish at this point and ask Dr. Szymon Nowakowski to continue the workshop. If you have any question or comments, just please write your questions or comments in chat. So thank you. And Szymon, the screen is yours.
Thank you very much. So I will try to share my screen. I think I'll do it like this, the whole screen, because okay, now I am doing it. The whole screen, because what I want to show you is how to get to the materials, to the workshops, and new tabs will be opening in my browser. So I need a whole screen. Okay, so if you we have prepared some material for this session and for the next week sessions too. And to get to the page with links, you need to search in Google or any other search engine that you use for Center for ML. This is short for Center for Machine Learning, and warsztaty or workshop maybe. And then you click on the provided first link. Usually works. You get to this page, and then if it is not the most current, because sometimes it is not the most current, you can click on this first listed event on the right side of the screen, and the very first event is the current workshop that we are in, and here are the materials. So if you click it, you go to the GitHub page, the materials. Actually, you can also start from the GitHub directly. You need to find the user that is called Center for ML. Again, it is Center for Machine Learning, and the repository is workshops, and you need to find a branch. This link that I showed you takes you directly to the correct branch, so it is easier. And then we will be here. You have the agenda, and there is some more material that we will cover today. Some more material is provided, and here this list gives you an idea of what will be covered and what will not be covered today. So we will cover the position 0, which is this introduction. The position 1, 2, and 3 will not be covered, and the 4 not. No, this is not numbered like that. So we will cover regression from number 3, but not cover the classification neural network example. But these materials are provided for you, and anybody who is interested, I encourage them to have a look and try to go through the materials not covered today too. So we will be starting with tensors. So from the GitHub, you click on the material that you want to have a look at. And then, this is important, you open it in Colab. We'll be using Colab to go through everything. Okay. So we are in Colab now. And whatever changes that you do to this and all the other stuff that we will be discussing today will not be saved. To save them, you need to click on, unfortunately, I have the Polish Colab, so you have to click on File, probably in English, and save the copy on disk. It will save the copy to your Google Drive. Or you can, for this is maybe for advanced users only, but if you prefer this way, you may create a fork of our GitHub repository with workshops, and you can save the copy into your GitHub fork. Okay, so there are two ways to save it, but you must use one of them to have the copy that you make changes to saved. If you don't, after you close this window, your changes will be lost. So the decision is yours if you want to save them or not. I gave you the way to save your changes. And I will be using another branch with solutions. I don't encourage you to use it right now. I think that it will be better if you use the branch without solutions at that point and try to work out your solutions. But anyway, the solution branch is available and the link will be provided after the workshop ends. So I will, there is this link. No, it is not this, sorry. There is this link. There is this link. Materials for day one are available in this repository, and I will give you, and the solutions will be available in this repository. I will give you the link to the solutions after the workshop ends. Okay, so the technicalities are covered from my point of view, but if any of you have any questions or maybe need me to repeat any part of this information, just please put your question in the chat.
Szymon, somebody asked
I
to
should put
put the link into
okay,
the
so
chat.
there is the link now. So the link is in the chat now.
Okay.
And there is one more message, so let me read it. Okay, it's taking it's taking very long. Using the link, I can't locate the zero tensors file for today. Let me see. So I'm clicking the link from the chat. Then we click here in this repository for day one. And then when GitHub opens, the zero tensors are on at the middle of the page, let me say. Or you can click the first link, it will get you to zero tensors too. So let me do it again, very quick for you, so that maybe any other doubts are covered. And then we open it in Colab. This is also important. We open it in Colab, and any changes that you make can be saved using file and save to disk. Okay. Okay, so I will start now, and if anybody of you have any problems, please write your message, and I hope that I will have a look in a moment again into the chat, but some other presenters from Center for Machine Learning or Interdisciplinary Modeling Center will try to answer your questions, I hope. So before we begin talking about neural networks per se, let me cover something that has become, I think, a common misconception lately, because in the field currently there is a departure from talking about neurons. So if you open any publication that is current, like let's say it dates from 2020 or is maybe more fresh, than that. Probably chances are like 90 or 95 or maybe even 99% that you will not find any mention of any neurons. Nobody talks about neurons nowadays. Of course, there are neural networks and they are called neural networks, but nobody talks about neurons in neural networks. The terminology has become much more mathematical. And I think that one reason behind it is that there are some very very strong architectures like transformers, attention, uh, and diffusion processes that do not use that there is not that you even you wouldn't be able to find an analogy of a neuron in that architecture. So it makes no sense to speak about neurons. This is one reason. And the other reason is that in fact, and there is a paper cited about it, that in fact a human neuron from the human brain, it is not an analog of a neuron from a neural network, artificial neural network, but rather it is a very complicated neural network per se. They say that to simulate a human neuron from a brain, you would need a 5-layer 128 unit temporal convolutional network, whatever it is not important. What I want to the impression that I want you to have is that a real neural network, the biological neuron, sorry, the biological neuron is rather an analog of a complex artificial neural network rather than a single neuron. So if such a mathematical language is emerging in this field, we must learn to talk about it without creating confusion. And the first part of my introduction, because this day maybe I should have also said that the first day is very introductory, so we will not be covering pins today. Rather, the aim and the objective of the first day is to give you a feel of that field and give you the language to be able to speak about the objects that are important in this field of neural networks, artificial neural networks, and also to maybe show you and guide you through the process of creating your first neural networks. We chose PyTorch as the framework of choice, but there are others. But to guide you through the process of creating your first, maybe not your first, but for some of you probably it will be your first neural network, artificial neural network in PyTorch. So let's talk about tensors. Tensors are the objects, the very basic objects in artificial neural networks, and they are basically just multidimensional arrays. But for a long time I was not a fan of this word tensors, because I come from computer science, and for me, for a long time, like let's say 5 years ago, tensors were just multidimensional arrays, and I didn't see any sense in calling them tensors. But now when those artificial neural networks evolved into those more complex architectures like transformers or diffusion processes or flow processes, it started to make sense to call them tensors, because these are not like multidimensional arrays from the computer science point of view. Rather, they behave like mathematical objects, tensors. So nowadays, I am totally convinced that it makes sense to call them tensors. And moreover, my experience is that when trying to speak about different dimensions of tensors, I very often created confusion, or somebody else talking to me created confusion in me, because we didn't use this terminology right. Basically, we used the computer science terminology coming from multidimensional arrays when we spoke about tensors, and it was confusing. Maybe I will show you why. So this is this is taken from a blog, but it's just a random blog. I really didn't have to search for it when I prepared it for this page for the very first workshop. We gave it, I don't know, probably 3 years ago, and I was preparing to that. I like spent 2 minutes searching for a blog that would make my point clear. So this guy here, and it is really not his fault. I am not saying that this blog is without. I am not saying anything wrong about this blog. I am just trying to show you that that without proper language we will very quickly create a confusion. So this guy speaks what is a one-dimensional, two-dimensional, three-dimensional, four-dimensional, and five-dimensional tensors. Of course, when you add a dimension, you need to, as you expect, a three-dimensional tensor would be a cube, and then four-dimensional tensor would be a group of cubes, and then a six-dimensional tensor would be a cube of cubes. So it is as expected. So then he says, let us define a tensor in PyTorch. And he defines a tensor, this tensor. And he says this creates a 2 times 3-dimensional tensor named as X. So he created, according to what he's saying, a 6-dimensional tensor. So let's have a look at this, at his tensor. This is the tensor that he created. Well, it is not a 6-dimensional tensor. It is a 2-dimensional tensor. It would be this guy here. So, so where is confusion coming from? Again, to make it maybe more clear, he's claiming that he created a 6-dimensional tensor, so a guy like this. But in reality, when we have a look, when we run this cell, we are seeing that he's creating this guy here. And the confusion is coming from the fact that he's mixing the dimensions with the indices that can be used to index a given position. So if you have a look at this tensor, it is an array of dimension 2, and to use this first dimension he can use 2 indices, and to index the second dimension he can use 3 indices. So basically this is this, and not being able of differentiating if we are talking about the number of indices that can be used, or we are talking about the positions when we use those indices, creates this confusion that is very hard to get off, and it becomes very quickly becomes hard to explain to somebody what tensor actually you have in mind. So to make it maybe more clear, let's fix our language for this talk, at least for our workshop. But I hope that you will use this terminology in your own work too. So maybe let's first discuss the multidimensional array terms. And when you have a multidimensional arrays, usually when you create a vector, it is called a multidimensional array, a one-dimensional array. A vector would be a one-dimensional array. And then when you are interested of the maximal index that you can use to index this guy, you would call it size of this array. But in mathematics, it is not working so well. For instance, a vector in mathematics, a vector from with n guys, with n positions, it is coming from r to the power of n, and it is basically considered n-dimensional, not one-dimensional as an array in computer science. Because we want our language to reflect mathematics rather than the computer science philosophy, we need to change that language from the multidimensional arrays into more mathematical language. So in tensors, the number of those positions would be called orders. So for instance, that tensor would be called a tensor of order 2 because it has 2 positions. That tensor would be called a tensor of order 1. This is a tensor of order 2, order 3, order 4, order 5, order 6. So not a dimension, it's an order. Order is 6 of this tensor. And the dimensions, they reflect the count of indices that you can use to index a given order. So it is something like a size in an array terms. So this guy is really, it is correct. It is 2 by 3 dimensional because it has like 2 dimensions can be used in this order and 3 dimensions can be used in this order. So this is correct that it is a 6-dimensional tensor, but it doesn't mean that it has 6 orders. It is a 2-order tensor with dimensions 2 and 3. And when you speak like that, it becomes very clear what tensor you have in mind. So again, this tensor is a 2-order tensor, or sometimes we say a tensor of order 2 with dimensions 2 and 3. Basically, if you have k orders, you need to provide k dimensions because each order can be indexed in a tensor. So some more examples. So if you have a tensor of order 0, it is just a constant. And of course, it doesn't have any equivalent when we talk about arrays. If you have a vector, it is a tensor of order 1, and it is one-dimensional. In arrays, you would say one-dimensional array, but we call it a tensor of order 1. A matrix with arrays, it would be a 2-dimensional array, but we forget about it, and we rather call it a tensor of order 2. And this tensor, it is an order 1 4-dimensional tensor because it has 4 positions in this first order. It is basically a vector from r to the power of 4. And maybe now let's go through this presentation that will give you some more information about tensors and basic neural network layers. And to do that, I need to go back here. I need to stop sharing the screen and show you a presentation. Okay, so I hope you can see this this presentation right now. And can you? I hope that you can see my my marker.
Yeah, it's visible. Tensors. It's okay. A single value or the zero tensor.
Thank you very much. So a single value, like a constant, is an order 0 tensor. We have already seen that, and to show you this guy here, I will use a block like this. It is this constant, a tensor of order 0. We can have some more guys, and if we have some more guys, they become a vector. In machine learning, usually they represent some features, like for instance, an age, height, and weight of a person. we measure the height, we measure the weight, and the person tells us his weight or her age, sorry. And this is a vector of features. Features are basically mm, the the qualities that we can measure and express as numbers in machine learning. And such a vector is an order 1 tensor. We can have more of them. Why do we have more of them? Because they usually come in batches. So for instance, we measure like 100 people. They tell us their age. We measure the heights, we measure the weights. So we have a bunch or a batch of vectors of features, and they create the order 2 tensor. So the batch dimension would be the batch order would be the first one, and the dimension indicates the size of a batch, and then and this is the usual convention. The batch order is the first one, and then comes the order with features. Sometimes they are not coming from a batch, but rather the same person comes, for instance, to a doctor at age 2, 4, 10, 16, 29, 40, and some measurements are made. So those features are measured for one individual, and they also create the order 2 tensor, which is just the features, how they behave in time. It is a time series. So a time series would be with features, with multiple features. In this example, 3 features would be also an order 2 tensor. And as you expect, we could have a lot of individuals. Oh, okay. So before we go here, we could have a lot of individuals, and there would be batch of such measurements in time. So it would be an order 3 tensor with batch as the first order. But we are changing the example now before we come to order 3 tensors. And the next example is that the features are the x, y, and z coordinates of a wrist movement when the person writes, for instance, letters of the alphabet. So that they would be writing A, B, C, and we would be measuring the movements of the wrist with some device. And we would take a note of x, y, and z coordinates, for instance, every 10th of second. So these would be our new features, x, y, and z. Also 3 features, but behaving and also it is a time series because it is happening in time. And this is also an order 2 tensor. But if we measure the letters for a lot of individuals, and maybe some of them will be writing more than one letter, so we make a lot of measurements of a lot of letters of how it happens for a lot of individuals. We get those measurements, x, y, and z, the features, in a batch. They are batched. So let's say we get 128 measurements of different letters in time. So this creates the order 3 tensor. Sometimes the order 3 tensor comes naturally when you have only one picture. So if you have only one picture, you have the height and width of that picture, but every pixel is colorful. So these colors are coded with 3 numbers, R and G and B. This stands for red, green, and blue values. This is the RGB coding, and it codes the color. So one photograph, one image would give you a order 3 tensor with orders being height and width and the RGB values. And in images, the R and G and B are not called features anymore, but to create maybe more confusion for the beginners, they are called channels. So in image processing, the features are called channels. But I believe nothing wrong would happen if you call it, still insist on calling it features, or if you use the word channels for time series, nothing wrong would happen, and probably you will not create a confusion. But anyway, the standard terminology is features for vectors other than images, and channels in image processing. So naturally you get order 3 tensor here, but as you probably expect, we could have more than one image. Like for instance, you would be training your network to classify image into cats, dogs, mice, bridges, airplanes, and trucks, and sport cars, and huts, or computers, or whatever. Like you could have like let's say 1,000 of class, 1,000 classes. And a million images, and then a group of images would be called a batch of images. So a batch of images is an order 4 tensor. And again, the first order would be a batch, then height, width, and channels. Sometimes it comes like a batch and then channels, height, and width. It depends on the coding, but the batch order is most often the first order, and then come the last 3 orders: height, width, and channels. Okay, so maybe before we go to neural network layers, maybe I would like to give you an idea that if you consider it not this first order, if you do not consider it a batch order, but rather you have these images happening in time, this would be the case of a movie. So let's say you have a movie with images organized in time. Naturally, a movie is an order 4 tensor, but a batch of movies would be an order 5 tensor. I do not have it on the presentation because it would be really hard for me to draw, but you can easily imagine higher orders of tensor. Actually, they are very natural, like this example with a batch of videos. A batch of videos is a very natural object, and it has five orders. Okay, so now let's go to a short introduction to the layers. And the first layer will be a linear layer. Then we will cover the convolutional layers, and that's it. Those 2 types of layers will be covered today. So linear layer is just a matrix multiplication. So let's go back to this example with batched images. So you have a batch size, let's say 128 images. So here we can see 2 and a little bit of the third image, but you can imagine that there are more, like 128, let's say. And you have the height and the width of each image, and the RGB channels are organized in this order here. So you want to multiply it by a matrix 3 by 2. So this dimension here, the dimension 3, must correspond to the last dimension of the the last order dimension of the tensor. Because when you do the matrix multiplication, let me maybe recall how it happens to those of you who forgot. It happens like that we take the first guy and multiply it by the first guy here, then we take the second guy and multiply it by the second guy here, and then we take the third guy and multiply it by a third guy here in this column, and we add them together, and this is the result. And then we repeat it for the next column. We could have more columns. So in this example we have 2 columns, and the result of this multiplication is a vector of dimension 2. So observe that this dimension of the matrix, it corresponds to the dimension of the last order of a tensor, and the result, the dimension of the result correspond to the number of columns in this matrix. Okay, and of course you can arrange those results as some new channels. So you have 2 new resulting channels after this multiplication. And if you repeat that process for each and other, for every vector that is present in all that structure, which is really complex and really multi-ordered structure, but it has very many vectors that are visible and can be selected for this multiplication. So if you repeat the same process for every one such 3-positional guy, you get a 2-positional guy as a result. And those 2-positional guys, they can be arranged in the same structure as the original structure. The only difference is that the last order dimension changed from 3 to 2. Why from 3 to 2? Because we multiplied it with the matrix 3 by 2. But if we used a matrix 3 by n, the result would be the last order dimension would be n. So after we can see this, we can understand and observe that the linear layer, which is just a matrix multiplication by a matrix, let's say n by k, creates from the last order with dimension n the same tensor. The tensor organized the same, with the only difference that the last dimension is k in a result. So n, the dimension of the last order n, changes to k because we use a linear layer which is a matrix n by k. Observe that I didn't use the word neuron in all this even once. This is the first time I did it. Okay, so a linear layer again is a matrix n by k, and what it does, it acts on a last tensor order, which are usually features or channels, and possibly it changes its dimension. Why possibly? Because this matrix can be n by n, and if it is rectangular, it will not be changing this dimension. But if it is not a rectangle, no, it's a square. Sorry, if it is not a square, rather it is a rectangle, it will change the dimension. And the order structure, so all other orders are preserved. Only the dimensionality may be changed for the last order. All the other dimensions, they remain the same. And in PyTorch, there is this convention that you can index things from the end using the negative indices. So you can, for instance, say -1, -2. And it is very convenient because this order that changes is the order -1, no matter the number of orders. If you have the, for instance, 5-order tensor, the only order that may change is the order -1. If you have, so 1 from the end. If you have the order 3 tensor, the any order that can change is the order -1. If you have the order, I don't know, 11 tensor, the only order that can change is the order -1. So it is very convenient, because if you had to count it from the start, this number would be changing every time you have a different number of orders in your tensors. Okay. So the convolutional layer, how does a convolutional layer work? So again, let's work with our image example, but this time we have a single image, just for the convenience of being able to speak how it works. And instead of representing it with those items, separated out items, it is represented like a block of numbers. So this is the height, this is the width, and there are 3 channels, R and G and B. And the convolutional layer uses something called filters, and the filters are K by K by channels blocks of numbers, like matrices. Maybe you can think about it like a 3-dimensional matrix, but it is a 3-order tensor actually. So it is a 3-order tensor, and the only requirement is that the channels here, they match. Those numbers must match. And so this dimension must be 3, like this dimension is 3. And K is usually a small number, like 3 or 5 or 7 or 11 sometimes. So if we have an image called with height 640 by, let's say, 480, still we use small filters like 5 by 5, let's say, with 3 channels. And what is happening in this layer is that this filter, it gets positioned here. Here is a match, so this dimension is exactly matching the dimension from the image, and we multiply everything by everything. So here we multiply K by 3 in the RGB with 3 channels example. This is 3. So K by 3 numbers from the filter by K by 3 numbers from the image. And the dot multiplication, it produces, it is summed together, and it produces one number. So as a result, we have one number. So this guy is a result of applying this filter to this position. And this filter, it is a convolution. So this filter is convoluted through the whole image. What does it mean? Is convoluted? It slides through that image and produces more numbers. So this is the 3rd number, the 4th number, the 5th number, and then it starts from one position down and produces the next number and next number, and so on. So as a result of this convolution, we get only one channel. Maybe I will have some. Oh yes, one channel, because one result in this order, but a new height and new width here. This is a new height and new width, and the formula for the exact value is quite complex. It depends on some other parameters than only width and height and the K. I mean the width and the height of the filter, because this filter may be moving not one by one, but for instance like it can skip some positions in the original image. It is possible to create such filters. For now, we need only to know that one channel, a new image with one channel and some new height and new width is produced. And this new height and new width, it can be computed from the original height and width and k and some other parameters. But this formula is a little bit complex and too complex to discuss it right now. And actually, you do not need it at that point of our acquaintance with neural networks. What, however, is important is that sometimes convolutional layers have more than one filters, because we need to have a result with more than one channel. So if you use 6 such filters in a convolutional layers, in a convolutional layer, sorry, you would get as a result 6 numbers and the same new height and new width for all of them. So they can be organized in such a 3-order tensor with new height, new width, and this dimension is 6 output channels, because we used a convolutional layer with 6 filters. And in general, you can use a convolutional layer with k filters. No, k is not a good letter because it is already used, with f filters, and as a result, you would get the dimension f as a result in this tensor here. And of course, the order structure, for instance, if you had a batch of images and you used the same convolutional layer, it would get preserved. So as a result, you would get a batch of images with a new height, new width, and some other, but equal in each image, equal number of channels. So observe that the higher order structure gets preserved. And in all this, probably you noticed that the same things are happening to multiple vectors or maybe tensors, or but the same thing is happening. So for instance, let me go back a little bit to this matrix multiplication. So here, as you can see, the same matrix multiplication by this matrix is happening for each 3-positional vector present in this high order structure, and this is true that it is happening. It can be computed simultaneously for all of those positions, and this is why neural network computations, training or inference, is so effectively done on GPUs, because GPUs are graphical processing units, the graphic cards that you probably, the game players, the computer game players, but everybody has a card in his computer to facilitate creation of the image on the screen, but they are also used for, of course, they are very powerful if they are to be used for neural network computations, but they are very effective because they make it possible to perform all those calculations simultaneously. So this linear layer multiplication, it can be computed simultaneously, and also this convolution, as in this example. It can be performed for a lot of images simultaneously, and this is actually the reason why they get batched, because if you compute the convolution for only one image, it takes some time. And if you compute it for a batch of images, it takes the same time because it is done in parallel, simultaneously. And this is also the reason that such or analogous computations in CPU, this is just the regular processor in a computer, CPU, computer processing unit, probably, or computational processing unit. The CPU, it is not able usually to process as many vectors and matrices simultaneously. So this is why the computations on CPU, they are much slower. Not because the CPU is slower than a GPU. No, it is usually much faster than a GPU, but it can process only a few vectors at once, and in a GPU you can do it massively. It is a little bit slower, but you process let's say 1,000 more vectors at the same time, and as a result you get a speed up of, let's say, 100 times. These numbers are just coming from my head now, but just to give you an idea why the GPU are so effective in neural network training. Okay, so the takeaways from the convolutional layers is that the dot product multiplication that is happening during the convolution with a filter, it usually acts on 3 last orders. This is the width, height, and the throughout all channels, and the filter is convoluted across the width and height orders. So it is convoluted. I mean, it is shifted through the width and the height, and the channels, it is not shifted because this dimension in the filter matches the dimension of the order in an image. And the higher order structure, it is preserved. The dimensionality may be changed only for the last 3 orders. So a new height and a new width is produced, and the new channel dimension is equal to the number of filters, because one filter, it produces one channel. So you have an option to use multiple filters to produce multiple channels. So this is how it works in neural networks. And are there any questions? Because I think that we came to the end of this part. Yes, and if you have any questions, I will be happy to answer the questions. You can write them in the chat.
Please have a look at
Yes.
chat. There are some free comments or questions.
Do we lose some information during convolution? Yes, actually, the convolution, yes and no, because the convolution, as I have described it, with a step of 1, is computed for each and every value in an image has some impact on at least some of the resulting values in a result. So if you change even one value in an original image, you would get some changes in the resulting smaller image, but with possibly more channels. Maybe not all of them will get changed, because that filter, it has only some visibility. For instance, when you move this filter, when you slide it and you move it to a far away position in this image, the change in of a given number, it will not have an impact on the computation done by a filter that is far away, but it will have impact on the filter that is in this position and in some neighboring positions. But still, this operation, it may not be reversible. So it means that the result that you have may be in a way for instance, when you compute an average, do you lose information computing average, or do you do not lose information computing average? When you compute an average of a few numbers, each and every number, it impacts the average. So in this sense, each and every number has some impact on the result. But on the other hand, you lost some information because from the average of, let's say, 10 numbers, you are not able to recreate those numbers, the original numbers. So in this sense, you lose information. I don't know if I answered your question. Why is it filled with the random values? Because PyTorch, when it creates a tensor, it initializes the tensor, and actually the tensor initialization is a complex topic, because let's so when you have a neural network that you want to start training, it is very stupid because it doesn't it never saw any data, so basically it will be behaving irrationally, in a human sense, I mean. But you want such a neural network to be able to we will be covering it maybe a little bit more in next sessions, but there are two phases of neural network training. The first phase is that you go forward with a data, you get a result, and then you compute something that is called loss. You compute loss between, so a value of a difference between what a neural network predicted and the ground truth that you know that is true. And then you have a backward pass in which you compute gradients in a neural network, and it is called the back propagation, and basically you want to go backwards with those numbers in a neural network. And the neural network that is really stupid and you want it to start training, it must behave at least in such a way that this forward pass doesn't produce crazily high numbers, and that the backward pass doesn't produce crazily high or crazily low, like very close to zero, like let's say 10 to the power of minus 30, or very large, like 10 to the powers of plus 30 gradients, because then with such very high or very low gradients you would have erratic behavior of the neural network, or you would have no training at all with very small gradients. And for a neural network to be able to start training with a data that it never saw, you assume that the data is normally distributed, and you initialize that neural network weights. So all tensor are initialized with some random numbers that with this assumption of normality in data guarantee you that the forward pass and the backward pass will not produce crazily high or crazily low numbers. So this initialization that you saw basically is automatic, and it is done with that in mind, to give that starting functionality for a neural network. Okay, so thank you very much. So if there are no more questions, we can let's make it 10-minute break. We do not have to stick to the schedule so tightly, so I suggest, because there will be two parts in what follows, so maybe we'll make another break after the first of those two parts. And now let's make a 10-minute break, so maybe a 13-minute break. So let's meet at 11:25 again. Okay. Okay, so it is time to start the second part. There is somebody writing a message, so let me maybe have a look. Yes, there will be a recording. It will be provided to the participants after, probably some time after this meeting ends, because it must be processed. The breaks will be removed and so on. So let me share my screen again. All right, and go to, where is it? Yes, here, but now instead of doing the zero tensors, we'll be doing the one computational graph. Let me have a look at the. Nobody is writing that they cannot see my screen, so I hope that everybody can see my screen, and I will just proceed. I also hope that everybody can hear me. Nobody is writing that they cannot. So again, we open it in Colab. I encourage you not to use the solutions. There will be some tasks for you during that part. Okay, so maybe not to lose time, we will just import those imports. And I would like to begin by giving you some background on that part of today's workshop. Why do we give it? Why do we talk about the automatic gradients? Basically, for people who just use neural networks from the engineering perspective, I mean, that knowledge and what will be covered today is not strictly like the first most important thing. It is not a must, but you will be using neural networks on the rest during the other parts of the workshop for training some physical laws, as Professor Lessing has described during this introductory talk in the beginning today. And it involves calculating derivatives with respect to some parameters of some functions, and the thing is that it will use the same engine that is used for neural network training. So I believe it makes sense to cover this engine and how and why it is there, how it works, and our idea behind providing this information was that it will just be important during the next phases of this workshop. So the thing is that when we design a neural network, we think in a forward manner. So for instance, those multi-layer perceptrons that were invented, I don't know, 30 years ago or whatever, they take a multidimensional data point, tensor of order 1 in our nomenclature, and they just multiply with some weights, apply some nonlinearities, and then they arrive to some result, and that result is compared against the ground truth, that value that we know that is correct. It is sometimes called a label. So for instance, we take the age and the weight of a person, and we want to predict the height of that person. So we would take this two-dimensional object, the tensor of order 1 with 2 dimensions, age and weight, and we push it through the network, multiplying it with some weights, some linear layers, some non-linearities in between, and then we get to the value of a predicted height, and then we compare it with the known height of that person, and we can see, okay, so we predicted 6 meters, but the actual height of that person is 1.50 meters. So we grossly exaggerated. So we must do something to our network that will correct that path of computations in such a way that the next time when we take the same person and we could calculate or predict the height, we will get into some value that makes more sense. And it would be great if we could get to 150, but we do not expect it on the first correction. But maybe let's not exaggerate that much after the first correction. So we would like that the network at least returns something like 4 or maybe 5 meters, but not 630. Okay, and how do we do it? How do we do that? The mathematical way to do that is to calculate gradient for that the derivative, actually the gradient of that loss function with respect to every weight, and it would give us the information. What is such a derivative of this loss, of this difference between the prediction and the correct value with respect to every weight of a the weight is maybe I should tell you that the weight is in a neural network is each value written in such a convolutional filter or inside or inside the matrix that is a linear layer. So each number in such a matrix is considered a weight of a neural network. So if when we know the gradient of a loss with respect to a given weight, this gradient gives us the information that if we increase that weight by a little bit, the resulting value will be changed in this or that direction. So for instance, it will grow a little bit or it will decrease a little bit after we increase our weight a little bit. And we have the same information because we are able to calculate the gradient with respect to every weight. We know for each weight in which direction we need to change it by a tiny bit in order to make our prediction a little bit smaller, because we predicted 6 meters 30 centimeters for a person that is the ground truth 1.50 meters. So we want to decrease that prediction, and we know, because we calculated the gradients, that in order to decrease that prediction we need to a little bit increase the first weight, decrease the second weight, a little bit increase, but much but by much smaller amount increase the third weight, and greatly decrease the fourth weight, and so on, because the gradient it indicates also the magnitude of this of the change that is necessary. So observe that after the computation of such a gradient, we are able to change every weight in such a way that our prediction will be better the next time, just as we want it to be better. And if we do it again and again and again and 1,000 times, our predictions will be great after 1,000 corrections. So this is basically idea behind the neural network training. And uh, historically, it was natural that people just calculated that gradient by hand. So they knew that, for instance, for a linear layer, the gradient is this and this, because it is a very simple transformation, a matrix multiplication, and the gradient is and the gradient with respect to a matrix cell is very straightforward to be calculated. But at some point, people became lazy. Actually, it happened in the beginning of a humankind, probably, but lazy in this regard, and they invented something that is called the automatic gradient computations or ability, and the very state of the art frameworks for machine learning, when you actually do the computations involving tensors, they make it actually not very easy, even rather automatic for you to calculate all involved gradients with respect to all weights that were used in this calculation. And in my opinion, it opened the possibility to create very complex neural network architectures, because before that, the architectures were rather very simple, because you had to invent the forward pass. So you had to invent what happens to the data when it is pushed through the neural network, like it is multiplied in this multi-layer perceptron. It is multiplied by those layers, and then some non-linearities are applied, and so on. And it is a really simple calculation, all in all. But after the automatic gradient was invented, and then you have to and then historically, and then you have to calculate all the gradients by hand. So you invent the forward pass, and you want it to be simple, because then you have to calculate all the gradients by hand, and you don't want them to be very complex, because then you will spend, like, I don't know, a year computing those gradients. But when automatic gradient ability emerged, it became possible that people only invent the forward pass, and it can be very complex, very complicated, to whatever the imagination of the engineers or scientists, whatever whatever they want, because the gradient computation is automatic, so it happens automatically. And this is the moment in time, the emergence of automatic gradients capability in neural network frameworks, that we can see some very complex neural network architectures emerge almost at the same time, like transformers, those diffusions, and so on. So we should have a look at this automatic gradient, because, as I said before, it is also used in pins as a way to calculate the physical gradient with respect to some physical variables. Okay, so here you have in those bullet points, you have again the description of what is happening in a neural network. And let me reiterate it. So let's say we finish the forward pass, and we get a prediction, and then we compute a loss value. Loss loss value is computed against the known ground truth. So basically we know if our neural network exaggerates or maybe makes the predictions too low, and we know if we want to increase or decrease that prediction. Okay, and then we compute or calculate gradients with respect to all weights of this loss function, and this gives us the information what is the impact of those weights on the loss, if the loss would increase or decrease if those particular weights were increased or decreased by a very tiny bit. And then we exploit it in backpropagation. We decrease loss, so we want to change our prediction in a correct direction, so we just and we want to decrease loss, so we adjust neural network weights against the gradient, basically, because we want our loss to decrease. So we always adjust the weights against the gradient. And now the question that occurs is actually at what point the gradients are computed. And the answer is that the gradients must be computed at a multi-dimensional point equal to the current values of the weights in a neural network, because these are the current weights, these are the current values of weights, and we want to know if changing the weights from here where they are now increases or decreases the prediction. Okay, so naturally, because the automatic differentiation engine, it is naturally used for machine learning purposes, the gradients always are computed at a point given by the tensor's current values. Okay, I think that now I should go and see if there are any questions. All good. If all good, then we can proceed. All good. No other questions. No other opinions. So let's have a look at a simple function, which is like this: x cubed and then plus y squared. We can calculate here in this example. It is very simple, so we can calculate by hand that the derivative with respect to x is this guy, and with respect to y is that guy. And concretely, we want, because this gradient, again, I want to stress it, it is very important. It is not like that this functionality, it gives you symbolic differentiation. No, it is not symbolic differentiation. We will never be able to tell with automatic gradient that the derivative of this function is this function. But we will be able to express that value at this point. Okay, so because the gradients are always computed in a point given by the tensor current value. So the derivative of this function with respect to x is 3x squared, and taken at x equal to 2, it is equal to 12. And the same that this other derivative taken at the y equal to 4 is equal to 2 times 4, which is 8. Okay, and in Python you would get it. So the points where you want to compute the gradients must be the values, the current values of the tensor. So we initiate the tensor like that. We say that we want a tensor x with a value of 2 and tensor y with a value of 4. Then we construct this function. Basically, we do it in steps. We could do it in one go, but I will want to show you something. So we do it in steps. First, we take x to the power, this is the power operator in Python. So we take a to the power of 3, then take y to the power of 2, and then add them together. So we get our f, which is exactly that. Let's also have a look at those fields gradient function. So in f, the gradient function is add backward, and in those two powers, it is a powered backward. So it kind of gives us the, actually there are, I can't remember the names, but there are some packages in Python that, or in or in PyTorch maybe, that enable you to have a look at this graph, because the computational graph is created during those operations, and here we just slide on the surface of this graph, so we can see that the first the F node is called add backward, and then the power 3 and power 2 node is called power backward. But you could actually, with those with those packages, you would be able to visualize that graph in full. But it is a little bit out of scope of this lecture, and actually I do not even know the names. I had a look at them some time ago, but now I forgot. Sorry, I cannot give anything more than this information that they exist. Anyway, the expression tree, it gets built as we go, and here is just to recall what are the values that are expected. And the thing is that the gradients of that function will be written to a grad field of those variables, x and y. Why is that like this? Because recall that this automatic gradient engine, it needs to be used in, this is why it was written, it is used in backpropagation. And in backpropagation, we want to adjust the weights by changing the current values by a tiny bit against the gradient. So we want to know the gradient. And optimally, it would be if the gradient was somewhere very close to the current value. So actually, it is realized like that. We have this tensor x with a current value of 2. Yes, we have a tensor x with a current value of 2, and to the grad field of that particular tensor, a gradient value is written. Okay, so now this backpropagation engine would be able to do something like that, correct this value of the weight by a very tiny bit. Step size is a tiny amount against the gradient. So a value of this multiplication would be subtracted from the current value. So something like this would be done in a neural network for each and every weight. And again, to be able to do this so easily, we need that value of a gradient written somewhere very close to the current value. And this is realized like that, because when you call f backward, so in this step we actually calculate the gradients by calling f backward. We calculate the gradients starting from this very top node f, and we go somewhere to the leaves of this expression tree, and the leaves are x and y. We get the values in the grad fields equal to 12 and 8, just as expected. 12 and 8, 12 and 8, just as it should be. Okay, so so far so good, but we usually do not have only single values, the scalars, the tensors of order 0. Rather, we have multi-dimensional entities, like multi-ordered, maybe I should have written here, multi-ordered entities. Most commonly, they are of order 2, 3, 4, 5. And in PyTorch, such two-dimensional matrices, they are called tensors of order 2, as we covered on the first part of this meeting today. And let's see what would happen if x and y were tensors of order 2. So basically, I just take another value for x, like x can be 2 or 3, and y can be 4 and 5, and I arrange them in a tensor of order 2, so like in a matrix 2 by 3. Okay, it is a matrix 2 by 3, and f becomes as before x cubed plus y squared. We print the f value, and the f value is this. So basically this calculation happens just as there was such a question in a chat. Usually in such tensor operations, they happen coordinate wise. So if we have like corresponding coordinates in those two tensors x and y, the value of 24 gets computed by 2 to the power of 2 cubed plus 4 squared. It gives us 24, and 3 3 cubed plus 5 squared, it gives us 52. And again, 2 cubed plus 5 squared, it gives us 33, and so on. Such computations are done usually coordinate wise. And why is it that? Because this is the most common way to do computations in the neural computations. Like for instance, applying those filters, it also works coordinate wise. But the problem is that when you call backward, you get an error. Actually, here you would, no, you are not getting an error because I need to put it here, f backward. It disappeared. You would get an error. Grad can be explicitly created only for scalar output, so I need to remove it, and then just we print f, which are those values that we discussed. And if I tried to run this backward, I would get this error. And this is not good. The problem is that you can call backward only on tensors that are scalars. And why is that? This is because the loss value that you compute at the end of the forward pass is actually a scalar. Even if you calculate the loss for a batch of images, or batch of people with some ages and some weights and some heights, the difference in total is just a number. And recall that this automatic gradient engine, it is created to actually do backpropagation, so it works only on scalars. It doesn't make much sense that it works on higher order tensors, but here we need it for a higher order tensor. And what we do, we just performs, I will explain it later, but we just sum those values, all of them, by running f sum on them, and then we get 277. You can check that it is the sum of them. And then we call, let's run it, and then we call backward on this sum. And now the sum is just a single number, 237. And this function is a function with a scalar result, so we can call the backward computation of gradients on it, and we get the results, which are exactly what we anticipated, because recall that in a point where x is 2, we would expect 12. When x is 3, we would expect 27. When y is 4, we would expect 8, and for y equal to 5, we would expect 8, and for 5, we would expect 10. And this is exactly what we get, because for the so we have 2, 3, 2, 2, 3, 3, and we get 12, 27, 12, 12, 27, 27. And here for y, 4, 5, 5, 4, 5, 5, we get 8, 10, 10, 8, 10, 10. So this is exactly what expected. That is as calculated by hand earlier, coordinate wise. That is on every coordinate separately. And maybe we should explain why this sum trick actually works. It works because as I explained to you, the computation, I use I and j as indexes for f. So I would change from 0 to like there are two possible values, and for j there would be its columns. It would have three possible values, but it works coordinate wise. So basically fij is a value at coordinate ij from x and y. Okay, so after you sum it and you calculate a derivative of the sum with respect to one of those coordinates, actually this is the same as partial derivative of the original function fij with respect to the same coordinate, because one coordinate has impact only on a result at the same coordinate. It doesn't impact any other coordinates in f. I am not sure if I am clear here, but if you analyze it, you will see that for instance x11 has impact only on the f11 result, not on f12, and not of f21, only on f11. It means that if you sum them together and calculate the derivative with respect to x11, you get the same result as if you calculated it for f11 only. So this is one why we can sum everything and calculate our gradients with the built-in functionality, and we get the same results as we run it separately for each and every coordinate. And observe also that it works separately of uh, not separately, independently on any tensors and any orders. So we just, for an example, used a 2-order tensor, 2 by 3, but we could use a 10-order tensor, 1 million by 1 million by 1 million by 10 million by 7 by 11, and it also would work correctly for this example. Okay, so maybe let me go here and see if there are any questions. I cannot see any questions, so either it is as confusing, my speech is is too confusing and everybody got confused, or everything is clear. Okay, I will just proceed hoping that everything is clear. So observe that those functions that we used, the derivatives were like the derivative of with respect to x depended only on x value. Where is the calculation? Here. So the derivative with respect to x, it depends only on x, and with respect to y depends only on y. So maybe let's create an example where the derivative with respect to x depends on y too, and let's see if we get correct results there. So we take the function, another function now, x multiplied by y, very simple, just to see this mechanism in action. And the derivative with respect to x is of course y, and with respect to y is x. And we do the same as before. I mean, we create x and we create y, and we multiply them to create that computational graph, and then we sum it, and to the sum we apply the backward to calculate the gradients in the grad fields of the corresponding tensors. And let's see what is the value of grad in an X tensor. It is 3, 6, 9, minus 1, 1, and 2. So observe that it is exactly as the value of Y tensor. 3, 6, 9, minus 1, 1, 2. I also to make it maybe more clear, I run such a comparison, and we get true, 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 true. Well, this is to be expected, because as we calculated by hand earlier, the derivative with respect to x of function f is equal to y. So we shouldn't expect, after the calculation of the gradient, which is triggered here, we shouldn't expect in the grad field, which we already know, after the calculation of the gradient, it stores the gradient value of the original function with respect to x coordinate taken in a value of current values of x and y. And we shouldn't expect anything different than the current values of y. Okay. Okay. Okay, great. It's clear so far. So let's go with another function. I want to show you how this gradient computational graph and gradient graph is actually computed. And for me, it was easiest to do on a blackboard or a whiteboard, but I do not. Actually, there is a in this environment we could use a blackboard, but I was trying to write anything and with a mouse, and it was not very legible. So so I prepared the scanned page with my handwriting, and we'll go through that together in a moment. But at first, let me explain why I chose such a function, because actually it was interesting for me. I did it for myself at the beginning, because it was interesting to see what happens if a node in x in this example is present twice in a derivation tree. Obviously, it should impact the computing of a gradient in a non-trivial way, because we all know that x times x, which is x squared, by the way, derivated with respect to x is equal to 2x, and x times y derivated with respect to x is equal to y. So this factor of 2 emerges, which is different in those two calculations. And I wanted to see if such a way of creating this computational graph, if it is able to handle such a case that we have the same variable present twice, because as I said, it needs to handle those gradients in a non-trivial way. Before we go to my handwriting, let's just notice that we should expect value 54 as a result, because this is, you can actually also calculate it by hand and see if so you have a function x cubed times y, you calculate the gradient with respect to x in a point given by two coordinates 3 and 2, and you should expect the value of 54. You can also do that calculation by hand before we begin. It is very easy, and I encourage you to do so to make sure that we should expect 54. And now let's try to go. I will stop sharing, and I will try to get to presentation. I need to close this guy. I need to. This is so we have this function. This is the same as x cubed times y, but for the reasons I explained, I don't want to create a graph of x cubed times y, but rather of x squared times x times y. And the graph is created in a way standard in computer science, that when you want to create a graph of some computations, you just every student of the first year of computer science, they do it. They when they it's a standard exercise. I think that given a calculation, you construct the graph of this calculation. Here we will enhance this graph of the calculation graph. We will enhance it with differentiation. This is something non-trivial and new, but the graph per se is something like regular first year exercise, I think. And for those of you who have maybe no computer science background, what you do, you select the first and the most important operation, and they are all, maybe not all, some of them are binary. I mean that they take two operands. Operands, I think it's operand is a correct word. Operands they consider they operate for two items, and some of them are unary in the sense that they operate for one item, like this x squared. The square operation, it operates only on one guy here. So you take the first one, which is this multiplication. You create two nodes. One node is y, and the other node is the rest of this expression. And you build from here. So in this expression, the main operation is this multiplication, and this multiplication takes x as one of its arguments, and the other argument is this x squared. With this x, let's wait for a moment, because we will have this leaf later lower in the tree structure, so we will connect it. But let's stop here for a moment, and now let's try to create a graph for x squared. So x squared, the main operation here is squaring, which is a unary operation. So squaring is a unary operation which takes x as an argument. So here is the graph. We connect this guy here now, because here we have this leaf, we can connect it. And we also need to name those nodes. So here are the names: F, J, H, I, J. These are the names of the nodes. I don't want to address this node as x, or this as multiplication, because I have two multiplications. So not to get confused, I use names for the nodes, which are the letters from F to J, F, J, H, I, J. So these are the names of the nodes. And for the leaves, I already know that the value, because the value is taken at the point x equal to 3 and the y equal to 2. These are the current values of those tensors. And as explained earlier, I want to calculate the derivative of f with respect to x, which is, by the way, this value at this point. This is important. I will not get the symbolic differentiation value. I will not see this function in any of these. I will just get the value of this function calculated at that point. Okay. So what we know is, we know the values for the leaves, and the value of this leaf I is equal to x value, which is 3, and the derivative of this node with respect to x is 1. And actually it happens for one leaf only. That leaf versus which, or with respect to which, we calculate the derivative. So there will be, in each derivation tree, no matter how complex, with million of leaves, there will be one leaf where the derivative is equal to 1. And for all other leaves, and here is an example, the leaf y, but there could be a z and whatever. So for this leaf, which has a name j, this is the node name. So the j value is 2, but the derivative is 0. And all other nodes or other leaves, which are non-x nodes or non-x leaves, they would have the derivative value equal to 0. So there is only one with 1, and all the others are zeros. And we can propagate through all the leaves, we can propagate the current values. Actually, the current values are known because these are the current values of the tensors. So there is nothing to propagate. We just fill the grad field with or maybe not the grad field, the temporary field with 1 for one leaf, and with zeros for all the other leaves. And then we proceed upwards in this derivation tree like this. So first we go from x to that square node, which is named h. H is just I squared. So observe that here, but also in the nodes above, I will only have the visibility to the most to the nearest two nodes, or to the nearest one or two nodes. I will not have the visibility to the lower part of the tree. So for instance, maybe let's before we start with this one and explaining this one, let's also notice that, for instance, this G node, it only sees H, which is the closest the closest node here, and the next node here I. The J node, no, the F node, it can see only J and G and J, G and J. It cannot see anything that is below in the tree, below those nodes. Okay, this is very important because it makes it very fast to compute this derivation tree. Okay, so now we covered the values in this node. So let's see what happens here. So here the value H is just I squared, which is 9. 3 squared is 9. So the value is simple. What about the derivative? So the taking to the power of 2, such an operation must know what is its derivative. And its derivative is 2 times I times the derivative of what is below. But those values can be taken from the most close tree, from the closest node from the tree. Observe that we multiply 2 times I value times the derivative of I with respect to x, which is 1, and we get 6 as a value. So here we store 9 as a value of this node, and 6 as a value of this node. Did we assume j is 2? Yes, we assume that j is 2 because this is the value of the tensor. In our example, we want to work with a tensor x valued 3 and tensor y valued 2. And then, yes, j is y0. J is just the name. J is just the name of this node. So you could think about it as a y value is 2, but as the name of this node is also j, you can think about it as the j value is 2. Okay, so coming back here, we have the values 9 and derivative value of 6, and we can proceed higher. So higher is multiplication. Multiplication takes it value by multiplying the nodes, the two closest nodes just below. So h is multiplied by a, so the value would be 9 times 3, 27. And the multiplication also knows how to differentiate itself. And the differentiation is you need to take the value of I, multiply it by a differentiate value of h, and add value of h multiplied by a differentiated value of I. But all of those 4 values, they can be taken just from the 2 nodes just below this multiplication. So for instance, the value of h and the differentiated value of h is taken from h, 9 and 6, and the value of I and the differentiated value of I can be taken from this node just below the multiplication, which is this. So you take the 3 and 1, and when you do this simple calculation, you arrive at 18 plus 9, which is also 27. But this is just the accident that they match. They do not need to match in principle. Okay, so we go higher. And you take f again. F is again multiplication, so we know what is the result of multiplicating, and we know what is the result of differentiating. It knows what is the result of differentiating itself. Again, it needs to get all those values that take part in this computation. It needs only look to the nodes just below itself, not to any part lower in the tree, and it calculates G times J is G27 times J, which is 2. The result is 54. Observe that this is exactly what we were looking to apparently, but this is just a coincidence, because what we were really looking to is the value of a gradient of f with respect to x, but it just happens to be 54 too in this example. So you take the value of j, which is 2, multiply it with the derivative of g with respect to x, which is taken from this guy here, which is 27, and then you add g, which is 27, multiplied with a derivative of j with respect to x, which is 0. So this term cancels out, and we get 54. And you get 54. And observe that this tree behaved correctly, even though the x happens to be twice in this derivation, which makes matters a little bit more complex. Okay, so we are done with this example. Are there any questions for this part, for this tree maybe? If no, we can proceed. And what remains is just a task for you that you calculate. It is actually a four-liner, so I think that we can spend like 5 minutes. You can spend like 5 minutes doing that, and then I will very quickly show you the solution. We want to calculate the derivative of x and y with respect to such to x and y. We want to calculate the derivative of this function with respect to x and y in those points. X is given by those coordinates, and y is given 0 by those, and in another two-dimensional point, this and this, 1 and 3, 1 and 3. So two derivatives in 2 points, and the function is like that. And in a maybe it needs some explanation that in PyTorch, to calculate the sign of a tensor, you need to call it like that, torch dot sin taken on x, which is a tensor. So first you need to initiate x with the current and y with current values, and then you calculate the torch sign of x in such a way, and then you divide it by something else. So please spend like let's say maybe now 4 minutes doing that to get those values, and we'll see together how to get them. Probably I was not showing you my screen, so maybe I will now correct this mistake. Okay, I can now go to this, but this is the task. it was also in the material, so probably you saw it, but so that everybody can see the same screen. Here is the task. Okay, maybe I'll switch for a few minutes. You have this task also described in the materials, and I can encourage you to do it, to spend this time doing that. And I will go to another screen to see the questions that maybe somebody wants to ask. You can see the graph drawing, yes, not the, okay. I will close it. Now is it better? So this is the function. These are the x and y values, and we need to calculate the derivative with respect to x and y at this point and this point. These are actually, observe the 2 points. These two guys are the same, and these two guys are the same. And to calculate the sign of a value, you want to run something like this. Okay, and I will go to the questions. Okay. Okay, so let me do it again. I am sharing the screen, and hopefully now it will be visible. I repeat, this task is also in the materials. Okay. So if anybody has any questions, please ask them. I will be switching to the questions for a moment, like in some intervals. So as long as there are no questions, I will be showing the task on the screen. Okay, I think that we can spend 2 more minutes on it until we are at 24 past 12. No questions. Okay, I think we can go through the solution now. As I said, it is really like a 4 or 5 liner. So first you need to initiate the x and y to those values, but those values, they must in a sense coordinately match. So the first pixel is the first p, I'm saying pixel because next I will be showing a plot. But the first point is 0.25 and 3. So it is organized coordinately as a first coordinate of x and y tensor, and then another point is 1 and 3, and this is also organized on the second coordinate of this tensor. So this takes care of the current values of the tensors. So it takes care of the point at which we will calculate the gradients. Then we create our function, which is sine of x times y divided by sine of x. Okay, and we do the sum trick because anyway those gradients will be computed for each coordinate separately, because this is the nature of running it on a sum, as I explained. And then let's have a look at the values of grad. So x is a tensor of order 1 with this first dimension equal to 2, so we can use 2 coordinates to call them, and the same happens to a gradient. So gradient also has 2 coordinates. So if we look at the coordinate 0 of a gradient of x, we can see the value of the derivative of this function with respect to x, because we are looking on x tensor, calculated for the first point, so this point. Because in Python, we index things starting from 0. So 0 is the index of this point. So in this point, the derivative has this value. And the derivative with respect to y in the same point can be read from the grad field of tensor y, and it has this value. And the same for the second point. We just need to look at another coordinate, and we get 2 other values. So actually I want you to appreciate that it is really a very strong result, because this function was quite complex. Actually, it has a discontinuity at 0.00, which is the 0 is outside the domain of this function, but still from the continuity of this function you can fill out this value. So this function is quite complex, and in those 5 lines you calculate the gradient of this function with respect to those 2 coordinates in some arbitrary points. It seems impressive, at least for me. Let's have a look at this function maybe. So this is this function with 0.00. It is filled with from the continuity of this function. You can fill the value of in the 0.00, and those 2 points that we were looking at gradients are those 2. They are located. The x is 0.25 and 1, and then y is the y coordinate is 3 for both of them. And let's have a look if the values of those of what we can see here, if it makes sense. I mean, in the sense of the gradients that we have. So the first for this point we have gradients like this. So the gradient with respect to x is negative, and the gradient with respect to y is positive. And in the second point, both of them are negative. So again, the gradient for this first point with respect to x is negative and with respect to y is positive. So let's have a look at this. So as maybe I'm not sure if you can see it very well. Maybe I should do something like this and maybe this and maybe okay to show more of this guy. So if you change x by a tiny bit in this direction, the value of the function it decreases and it increases for y. Yes, if you change y by a tiny bit, you increase y in a tiny bit, the value of this function increases. And in this point, if you change x by a tiny bit and y by a tiny bit, the value of this function decreases. Actually, the exact values or the proportion of this decrease or increase, we know it because it is represented by those four values. But really we automatically we were able to assess the behavior of this function in these 2 points. Actually, we could do it for more than those 2 points. What would be needed would be only to initiate those x and y tensors with more values, and this computation would be done in all of those points of interest. So I want to leave it, and I want to leave you with it for the next 10 minutes, so that you can contemplate it and maybe spend some more time with it, playing with other values and maybe having a look how it all how do I stop this? How it all behaves, and let's let's start at let's start at exactly 1:45 for the last session. Okay. All right. So we should be restarting our workshop. After the break, welcome everybody again, and let me go to, I need to share this, and we go to this Colab material. It is called 3 simple MLP like multi-layer perceptron in regression. It's important because there in the materials you can also see the material for the classification on MNIST. And it is interesting. It is more or less done in the same fashion as this regression material. So if anybody is interested, I encourage them to go through this material too. The difference between classification and regression basically boils down to the loss function that is used, and to have an idea on the loss functions and how to use them in PyTorch. There is also this material that we skipped, which is called 2 loss functions. So those 2 got skipped, and here we are in this third simple MLP regression EPINP. So let's go there. I will maybe I'll have a look if there are no problems. So probably everybody. This is what I was looking for. Okay, so I already clicked this because it takes some time to import. We are importing PyTorch by doing this, and some NumPy and matplotlib and math, which are just helpers. The PyTorch is the most important for what we will be doing. And we will work with the multi-layer perceptron in this workshop. Multi-layer perceptron can be visualized like this. I took it from somewhere. from where. I am not telling you where. Probably the reference is in the mm, mm, maybe it should be present here also. I think that from Wikipedia. So first the data comes, and each in that standard nomenclature, when we use neurons, each feature would be called a neuron, and then those neurons would get multiplied by some weights, and we would get another neuron values, and then some other multiplication. Everything gets multiplied by some weights, and we get some other neurons as a result. And then there is the final layer, which just multiplies those guys by some other weights, and we get the final output value, which is also a neuron, and is called an output neuron. And in between those weight multiplications, we would get we would use something which is called mm, a nonlinearity, or it is sometimes called also an activation function. So after each multiplication by weights, we would have an activation function, which must be nonlinear function. And the first question to you, because those multiplying by weights, as you already know, this is a linear layer, so it is in fact just a matrix multiplication. So if we forget about neurons, as I encourage you to do, we get an input tensor here, which has, for the discussion at that point, it can have order 1, so it can be a vector with some dimensions. You multiply it by this matrix. This is equivalent to multiplying by weights. So you multiply it by a matrix, then you get the result. But in between, you must use this nonlinearity, because then you multiply it by another matrix and by another matrix. So in between, you need to multiply it by some nonlinear functions. Maybe not multiply it, but you have to apply some nonlinear functions. And why is that? Why do you need those nonlinear functions in between? This is the first task. What is the purpose of the nonlinearities in between the layers of the neural network? So this is a question to you. So if anybody cares to answer, I will be very happy. I encourage you to try anything, because there are no wrong answers, there are only wrong questions, and I encourage you to try to give an answer, even if you don't know, especially if you don't know. Yes, this is basically the most important reason. Thank you, Jakub. That's true. When you apply linear matrix multiplications, one sorry, one after the other, you could actually do it in one step. Just multiply the input by one linear matrix, which is a composition of those three, and you will get the output, which makes it actually no sense to use more than one layer. And the other answer, but it is in fact the answer that that maybe a more detailed answer, because this is actually the full answer, the one given by Jakub. But maybe a more detailed view at that is that if you had no nonlinearities, the expressing power of such a network would be very poor. Actually, you increase the expressive power of the network by using more layers, and with those nonlinearities in between. So why is it? So because the number of parameters grow. With each layer, you have more parameters. But to use all those parameters effectively, that they do not degenerate into just one matrix multiplication, you need those nonlinearities. Also, those nonlinearities give you give you the ability to express nonlinear things with your network. So they are crucial. So we will do the regression. In regression task, we will build a network that predicts the result of a function. Why the regression, not the in classification? You want to classify the input vector into a class. For instance, you want to have a look at the RGB image of a lung X-ray and tell if it is a tumor or no tumor. So there would be two classes. Or maybe it's an image taken with a camera, and you want to say if it is a dog, a human, a cat, a horse, or an airplane. So this is it would be a classification, but in regression you just want to predict a number. And why do we want to do regression today? Because in physics you usually have functions that as a result have numbers, not classes. So for instance, you could use a pin to predict an energy of a system or to predict some other quality of a system, but all of those tasks in physics, or maybe not to be so strong, almost all of those tasks are regression tasks. So for there is a nice notation that I want to sell you for the multi-layer perceptron. So if X is an input tensor, then you multiply it with some matrix Wy. You add, it's called a bias vector, because this is actually not only I explained it earlier as only a matrix multiplication, but in fact you also add a small vector of biases. So it is like a linear function but with a shift. So you add this vector, and then the nonlinearity that we will be using can be expressed as taking a positive part. So if it is negative, you just change the value to 0. But if it is positive, you don't change it at all. And this nonlinearity is called ReLU, like rectified linear unit. And I encourage you to read more about it. There is no time for it today. So ReLU is just taking a positive part of a tensor, coordinate wise, and then you take this value after nonlinearity, and again you multiply it with a matrix W2. You add a bias vector, which is B2, and then again you take the positive part, meaning you apply ReLU to the result. And again you do it the third time and the fourth time, so you get 4 layers, not 3 as some. It's a 4-layer perceptron. Actually, there is a mistake here. And this is a nice mathematical notation of how such a perceptron works. It's a one-liner notation, so it is nice. And then we will use automatic gradient as we described earlier. We will use MSE loss, mean square error. Again, it is a mistake here. We will use a mean square error. Cross entropy is used for classification, and I encourage you to read more of on those subjects in those materials that start with number 2 loss functions that we skipped. And now we must select a function for the workshop that we will try to model with our network. And I thought that since we worked with this function and we saw it, and it is quite a complex function, So maybe it's a good idea to work with it for this workshop. So we will work with the function sine of x times y divided by sinus of x, and on a rectangle from -3 to 3 squared. So x can change from -3 to 3 and y can change from -3 to 3. Why is that? Because then sinus zeroes out on a p value and on a pi value, and the pi value is 3.14 something something. So we want to be safe in the area that the denominator doesn't zero out. There is an exception of denominator zeroing out at x equal to 0, but actually this, as explained earlier, doesn't constitute a problem, because we can extend this function at those points from the from its continuity. Okay, so let's have a look at this function again. This is the same function plotted here. So we will be. It is quite complex. It is changing rapidly at some points when we approach 3. Because we are close to 3.14, which is pi, and then sine can zero out, and it creates those large values or very small values. And to be able to work with neural network, we need some training and testing data. So we create it right now. We basically randomly sample our domain, which has 2 dimensions, and this rand d, it samples from 0 to 1. So if we multiply it by 6 and subtract 3 from it, this data is sampled from between -3 to 3, so from our domain. And then we can calculate function values, which is we take the first coordinate from this domain, which is x, times the second, which is y, and divided by the sinus computed on the first coordinate, which is x. So basically, this creates our data value, and we can visualize them. We do it by plotting those points, those 2 coordinates, 0 and 1, with red dot for the training set and black dots for a test set. There is something wrong with this code. I don't know what right now, but it works okay. Okay, no. Now I understand. I can explain it to you in a moment. So it takes a moment, and it is plotting first the training portion of the test set, which is 1000, and then from 1000 to 3000, we plot the test set with black dots. And it is taking a moment. Maybe I should not be running it. I wish I should be using what I already have computed. Okay, we will go back to it to see how it got sampled. Okay. So here you can you can see it. So again, the red dots are the training dots, and the black dots, they are the testing dots. Okay, so we covered the area from -3 to 3 on both coordinates quite nicely with the points, but here the function does not change very much, and here the function changes rapidly, and here note that we do not have any training samples at that portion of the function, and we'll see what happens with the ability of the network to learn that function in this area. And in this area we have some training red dots, so probably the network will be able to learn the shape of this function better in this area than in this area. But all in all, we'll see what happens in a moment. Right now, it is just a technicality, but we need to wrap those data tensors into something that is called the data set and then a data loader. So, are there any questions? Okay. Here are the answers to the previous questions. Thank you, Pavel. Why are some points of the surface? I don't know. Are they? Maybe they are because this plot, observe, is created from such rectangles. There is from a grid, which is this grid was created here somewhere, probably here. This mesh grid from -3 to 3, and 0.05 was the step, or the basic lattice step of this grid. And the thing is that especially in the areas that this function fluctuates widely, this grid may not be adequate, and I think that this is the reason that some of the points are off the surface. I think so. I didn't actually notice it before. I was looking at this part of the diagram before, not at this part. Sorry. Okay. Anyway, we need to wrap those things, and we do it by applying tensor dataset to our domain, which is presented like this. First come the x and y coordinates as the value that we always know, and then the function value, which is a label value, the ground truth value. Okay, the ground truth value. So always you create the data set in such a way that first you provide the training data and then the label data. Okay, and we need to create two data sets, because one is the training data set and the other is just for testing. We want them to be different. We do not want to test the ability of the network to represent this function on the same set that was used for training, because we expect that at those points the network will know what the function value is. We want to test it on some new points. So the new point is what is kept in a test set. And then you change this data set into a data loader. It is also a technicality, but it is necessary. And we do it by telling PyTorch to group the data in batches of size 128 and shuffle it during training. So each epoch is one full go through the training data. It's an epoch. It's a very important concept in machine learning. Epoch is one full go through all the batches in training data. And then after you finish it, take the last batch, which may be smaller because we have 1,000 training data and the batch size is 128. 1000 does not divide by 128, so the last batch will be smaller, and then after last batch we finish the epoch and we start the new epoch, and this new epoch will be shuffled again. So this shuffle parameter tells you to present the data in a more random way. It usually helps the neural network training. It stabilizes it. And then for the test loader, we do not need to shuffle anything because we are just interested in the final loss value on a test set. So what is the mean square error of our predictor, of our regressor, of our neural network on the test set? Okay, so now we shall have a look at the training labels. So this is the way that we go through the train loader. Okay, the data loader is usually enumerated in such a loop. So you write a for and you take the data from the train loader and you divide the data into two parts as they were initially divided. The first is the input to the neural network and the other one is the ground truth output. It is called the label in machine learning. And I am having a look at first 5 batches. So observe that the batch constitutes of 128 values. I am visualizing labels. So of 128 function values. Okay, this is the batch. 129 8 function values organized in a one order tensor. This is very important. Usually the organization and the number of orders in a tensor is very important. And we shall see it in a moment that we have an error because we do not control it efficiently or enough. And your task now, why do not I have the code for it? Maybe I am using the, let me see what I am actually using. No, not this. Yes, I must go to solutions, sorry. Let's go to solutions and restart it. Sorry about this, because I need the solutions. I do not have time to write it again from scratch. And what we need to do is to restart it. Sorry about it. It will just take a moment. We restart this. And we za dużo sesji trzeba pozamykać. Na pewno to mogę zamknąć. Okay, let's restart it. Sorry about it. Okay, it seems to be doing something right now. We do not have to visualize it. We need to generate our domain. We do not need to visualize it at this point anymore. And we need to wrap the domain into dataset and data loader. And let's see if the visualization works. Yes, it does. And your task would be to visualize the inputs of the network. So observe that a single label is an entity, is a constant, is a function value. So it is an entity of order 0. But if you batch it into batches, it is a vector, so a tensor of order 1. The first and the only index available for to index this guy is the number of a sample in a batch. And now your task would be to use a code similar to this one that you have in your scripts in no solution part, and generate and try to visualize and generate the input labels. And inspect the number of orders in the input labels. So I encourage you to take a moment to do that. You actually need to copy that code from above and change it just a little bit, and just the portion just the batch number 0 is enough to be able to inspect the number of orders. So let's take just until it changes to 12. For those of you who want to do that, maybe I'll go and see if there are any questions now. Okay, so I encourage you to take this time and to do it. And now we'll do it together. The code is very simple. I just want to print. The last time I printed batch labels, and now I want to print batch inputs, yes? And batch inputs, they would be organized into observe a tensor of order. Question to you. Nobody's writing. The tensor of order 2. You can see it by looking at the number of opening brackets. This is the tensor of order 2 because the single input to the network is 2 points, x and y. So it is a vector, a tensor of order 1, a vector with 2 coordinates, x and y. And when you batch them, you get a tensor of order 2 with 2 possible positions for indexes. The first position is the index for batches. You can use a number of a sample in a batch as an index. And the next order is the order for coordinates for those features. There are 2 features. The feature number 0, because in Python we enumerate things starting from 0. So the feature number 0 is x, and the feature number 1 is y. And for the next batch the same, and for the next batch, not next batch, next sample, next sample, next sample. And I printed only one batch here because I used if I equals to 0, so it prints only one 0th batch. Okay, 128 pairs of numbers, x and y coordinates. And here is the explanation again, maybe in another language, maybe it will be more comprehensible. Each data point was initially a 2-dimensional point. This is a vector or a tensor of order 1. So when we batch them, we have a tensor of order 2. Okay. Now we want to define a multi-layer perceptron network, and it is actually very simple definition. So we will use a sequential layer. It can be considered as a separate layer, but it is a layer, like a layer which is a container for other layers. So the sequential layer will have some layers inside. So the sequential layer will be composed of a linear layer, then a ReLU, then a linear layer, then a ReLU, then a linear layer and a ReLU, and a linear layer and no ReLU is needed. Is needed on the outside. You could use a sigmoid if you wanted, just change it into a sigmoid if you want to play with it at home. Observe only that I must provide the size of this linear layer. Those sizes here are the dimensions of that matrix that is used for this matrix multiplication in a linear layer, as I explained earlier when we had this presentation on layers. And recall from that presentation that if the entering tensor has the last dimension equal to 2, like last order dimension is equal to 2, like here, we need to have a matrix which is 2 by something. So it is very important. We couldn't use any other number here than 2. And then we produce a guy which has a dimension 64. And then the next layer, since it takes as an input the result of this layer, so it will take a guy which has last order dimension equal to 64, also must have the first the first dimension equal to 64, and then the last can be chosen arbitrarily. I chose 128, but when I choose it to be 128, then the next one must start with 128, and then this can be chosen arbitrarily. I chose 16, so this network basically magnifies the data first, changing the last dimension from 2 to 64, then from 64 to 128, and then collapses them from 128 to 16, and then to 1. So as a result, we get just one value as a result of the last layer, because this dimension of 16, last order dimension of 16 gets changed into 1. Okay, so we get one number as a result. No questions so far. And then we have a dropout layer, which is just to show you that the mechanism in a forward function. Forward function is this function that we need to write ourselves. It is the forward behavior of the network. So when the data is usually coded as X, maybe I should call it as data, input data. So when input data, because I don't want you to confuse X with the X and Y that we have in input data. Usually you do it in such a way, you code it in such a way that those layers act on input data, and the result is also called the same. So you take that input data, then this sequential layer, all those layers inside the sequential act on input data, and the result is input data. Then you can apply dropout to the input data, and the result is input data. And you could have much more layers in your network, and you could be applying them here. So here you could be, for instance, applying again a dropout to the same data. I am using a comment, but just to give you an idea, it could be written like that. So dropout on input data. It would mean that first you go through this sequential, and then you twice apply a dropout. Okay. Okay, and this is my my multi-layer perceptron, and I also defined how to push data forward through the network. And as I explained on the first part, or maybe the second part of this workshop, we do not have to care at all about the backwards part, about the gradient computation part, because the gradients, they will be computed by the engine for us. So this is the beauty of this. You can implement or define or imagine any complex computations that you want, anything, no matter how complex it is. You just implement the forward pass, and then the gradients, which may be very complex for complex forward pass, get computed automatically. Okay, so now we do training, and here I present you with a very short, but actually a full training loop that is used in PyTorch. So maybe you will sometimes need some other functionality in between, but it will be mostly technical. This what is shown. It takes care of everything that is important for training neural networks in PyTorch. So first we create the instance of our MLP object, which is a class. So this net is just a neural network, an instance of a neural network. And we take something that is called an optimizer, and optimizer, it is something that will fix our weights for us by those tiny bits resulting from the gradients, and we tell it to use the learning rate of 0.0011, 1 divided by 1,000. It is important that the learning rate is small, so you even if you have large gradients, you do not change the weights by much, only by very tiny bits, because remember that gradients are just the shape of the loss landscape only in that point that is represented by current values of weights. If you go very far from it, the loss landscape may be very different. So you do not want to take very large steps, because you do not have, actually, by knowing the gradient in a given point, you do not have the idea how the function looks far away from this point, even if the gradient is has a large magnitude in a given point. Then you tell the network that it is in a training mode, so you change. It is actually important only for layers such as batch norm or dropout. We do not have batch norm layers, but we have one dropout layer, and the dropout layer, it behaves differently during training and differently during inference. So the network must know if it is in training or in inference or testing, and you do tell it by changing it. And then you run 8 epochs, and in each epoch you basically enumerate the train loader. So you go through all the batches in such a way that you zero all the gradients involved. Then you put the inputs into the network and you push them through the network. This line, it calls the forward function, the forward method that you implemented. So in this line, basically all the inputs, all the batched inputs, they go through the network and you get the batch outputs. Then you calculate loss between outputs and the labels, which are the ground truth. And then we print them. This is for ourselves. We do not need it. And then we call the function that we all know very well. It calculates gradients for us of loss versus all weights of the network that are involved in the computation. And then we tell the optimizer to do one small step correcting the weights against the gradient. So actually this line, this is the line that updates the network. And then it is done in a loop. So so this is done for every batch, and we do as many epochs as we want. And this is basically it. After that, we should have a trained neural network. But it does not happen like this to be a case, because we get a warning, which is actually quite common, that there is something wrong with the input sizes of the tensors involved. And as we do not have much time, I'll just explain what is the problem, because as you saw here, from as an output, so this linear layer, it takes a tensor which is two-order tensor. The first order is batch, and the second order is has dimension 2. And as a result, it produces a tensor which is also a tensor of two orders, and the last dimension is 64. Here last dimension is 128, here is 16, and here is 1. So here you have actually a tensor of order 2, which has last dimension equal to 1. But the labels, the ground truth labels, as we have seen before, they are not the tensor of order 2 with last dimension equal to 1. Rather, they are the tensor of order 1. So this last dimension in the result of this network which is only a single number, so it can be indexed only with 0, is confusing this loss calculation, and we must get rid of this dimension. How do we do it? I will not show you that. I just when I get the outputs from the network, I squeeze the first order in, because this order is of dimension 1, so it basically is only a number, and I squeeze it and remove it from the tensor. And as a result, after that, now output and ground truth labels are tensors, are both tensors of order 1. is to say vectors. And before that, the outputs were the matrices with only one column. And now they are, after that squeeze, they are both vectors. Okay, and this is important because this loss, it got confused, giving us those warnings. So okay, so now I am able to run it. I am running 500 epochs, and I am not very happy with what is happening. This loss gets it is very high all the time, and it doesn't want to stay low. I'm not very happy with that. The idea here is to change the dimensionality to 1024. Why do I use the powers of 2? I don't know. Probably it is easier to fit such structures into GPUs, which also have all the dimensions inside expressed as power of 2s. I don't think that it is very crucial, but it is just a common way to do it. So what happened here is I added another layer in between. Look, I changed the dimensionality to 1000, and then from 1000 to 100, and from 100 to 16. My expectation would be that it will greatly increase the expressive power of this network because it will have much more parameters, and it will have a much greater expressive power. So let's run this. Okay, so there is the training. The training loop is just in this code that I run. And now have a look that it got low and stayed low. It stayed in the range of lower than 0.1 all the time. So it is much more satisfying than those 500 epochs with a smaller network. I hope you can appreciate it. And I want you to do something else now. I want you to comment this line and run it again and see that the loss, as I said, it doesn't get lower, because I said that this moment is the moment that we correct our network by tiny bits. And we don't do it, so it doesn't get lower, but it changes. Why does it change? Do anybody of you have an idea, or maybe it doesn't know and can wildly guess? This is much appreciated if you can do it. Why it changes? Maybe it should stay the same. I didn't see that comment. I'm not sure if playing dropout after MLP is a good idea. Yes, probably you are right. I just wanted to show you how to apply those two layers, one after the other, in a forward function, because otherwise we would get only the sequential, and the forward function would be very boring. So I wanted I used it as an excuse to show you a more complex forward function. Loss is computed per batch. Yes, this is true. Loss is computed per batch, so we get different values because in a batch we have different numbers. And another question emerges. Have a look here. So for epoch 0, the batch number 0 has this loss, and apparently the same network for the same batch number 0 gets another loss on the second epoch. Why is that so? Okay, each batch is different, so it explains different numbers in this portion. But why do we get a different number here? When we start a new epoch, a new go through full data. So again, we get batch number 0 and we get a different number. Why is it so? That's because we shuffle. Yes, that's correct. That's because we shuffle. So the batch number 0 on the next epoch may be totally different and is totally different than the batch number 0 on the first epoch. So this is why you get different numbers. That's correct. And now if we uncomment this, we get a network that actually learns something. And again, in the beginning of the learning process, the network is just randomly initialized, but in such a way that it expects data to be more or less normal, and the process of training can start. And then when we are close to the end of the learning process, the network is trained, so it knows the data, it knows what to expect, and it has predictions and the gradients quite close to nice to nice values, and it behaves well too. So in the beginning, it is very important that the network is initialized randomly, but not totally randomly, but in a sophisticatedly random way, such that it behaves for unknown data, not erratically. Okay. Okay, so now there is a training with a scheduler, which I will skip. I will not bore you with that. You can go through it on yourself. The scheduler basically changes the learning rate after each epoch. So this learning loop is different from the previous one only with this definition of the scheduler, and then the scheduler step after each epoch. And this scheduler step, it decreases the learning rate with each epoch. Basically, the thinking here is that the farther in learning you are, the closer to the true solution you are, and the smaller steps you want to do when you change your network by those tiny bits. Okay, so you can experiment with that. You can experiment also with different schedulers, because here I use this scheduler, and I give you some references to you can read about different schedulers, and you can experiment with those schedulers and see how they fare. And now we will test our network. So testing is very simple. I do it manually, although there are functions that do it more automatically. I just want to show you how to do it. So first you tell the network that it is in the evaluation mode. It is important for those layers such as batch norm and dropout, which behave differently on evaluation and differently during training. And then you run the code with torch no grad. This is telling the PyTorch not to update the gradients, because we do not want our network to learn anything from the test set. We want it to be agnostic to the test set. So this is why we, just to be on the safe side, we tell Torch, do not calculate any gradients during what we will be doing next. And you enumerate test loader. And as before, you take a data point, which constitutes of X and Y. You take the Y coordinate. You push this data point in the forward direction through the network. You get a prediction, which I label Y hat here. And you calculate the difference between Y hat, the prediction, and the ground truth Y, in the sense of a squared error, and you sum them. So this is a very manual process of calculating differences between the prediction and the ground truth values and calculating very manually a mean square error. Just to show you that it is possible too. You can do it manually. And you arrive at the value of mean square error 0.005, which actually you want to take a root square of, because this root mean square error is in the same units that your original units. So per average, we make a mistake of 0.2 predicting the function values. Okay, here is the same loop for the scheduler network. I will not be running it. Here I want to show you the visualization. Actually, I do have it. I do not need to run it. Of the predictions, which are green, versus the test set, which is black. And just for reference, we will be also marking with red dots our training set. So training is red, the black is a ground truth, and green is the prediction. So look at this area that the function is really flat. Not much happens for this function. Our predictions, the green dots, are totally well aligned with the black dots, so no difference here. When this function starts to fluctuate some more, the differences become larger. Actually, in these areas where we at least had some training values, the differences are large, especially in these areas where the function fluctuates totally widely. But we have some training points. The differences are large, but at least something was predicted close to the correct value. But in these areas where the model cannot know what is the ground truth function value, because it doesn't have any training examples here in this part, it actually is unable to predict the black dots. I don't know where the corresponding green dots are, but probably somewhere here. So here the errors are much larger than here, because here there is at least one training sample close by, and here there are no training samples in this area, so the network can only widely guess what is happening in this tail here. Here we have some training samples lower, so again the network is unable to predict those testing values higher than them. And that's it. I think for having a look at the results. I want to show you very quickly how to move computations to GPU, because I don't know if you noticed, but we were not using GPUs in the part here. Any questions? Any questions for what we have covered before? No questions. So I will just tell you that for now we have not been using GPUs. So the training is possible on CPUs, but we will see that for the GPUs it is much faster, and for reasons already explained, because the GPU per se is slower than a CPU, but a CPU, when you train it on a batch, it needs to take each sample from a batch and separately push it through the network, then it calculates those gradients and so on, and it does it separately for each sample, even if a batch is larger. This forward pass needs to be done separately for each sample. And even though the CPU is faster than the GPU, when you put the batch on the GPU, all those calculations, they are done simultaneously. One calculation would be slower, but when you do 128 of them, as we have a batch of 128, it happens much faster. And a result is that in the end of the day, you get the training finalized much faster than on the CPU. And this is why it is so important that the GPU is as large as possible. So now we have the GPUs that have, I don't know, 100 gigabytes of memory, and this is the larger the GPU, the faster you can do the training on them, because the more data you can put into the GPU at one time, and the computation, it happens simultaneously. Okay, so we want to learn how to move computations to the GPU. So first we just check if we have the GPU available. We do, because we are connected. Just a moment. Here you could get, if sometimes it gets disconnected, so you can connect to a GPU and even to a very strong GPU and even to some other units which are deprecated, but deprecated because there is the TPU version 2. So these are some other processing units that are that can do massively parallel neural network computations. But we use this one, which comes free and is the for this presentation it is enough. But anyway, if your execution environment were disconnected from the GPU, you might want to connect it to work with what I will be showing next. So first, we make sure that the CUDA is available. CUDA is I don't know, it stands for something, but now I cannot remember. And here is the explanation how to change the runtime that it makes a GPU available for you. And then you want to use a string CUDA or CPU depending on your CUDA availability. So now this device string will be set to CUDA because we have CUDA available, but if it is not, the device string will be CPU, which will put all computations on the CPU, because the code that I will be showing you is very flexible in this regard. So the code that I am showing you is able to run computations both on GPU and CPU, and it decides where the computations will be run in these 4 lines of code. So this is where it gets decided if the computations will be done on CUDA, it means GPU, or CPU. So how do you put a linear layer into a GPU? There are 2 ways. You can specify a device when you construct a linear layer, and you tell the linear layer that it should go to a given device, which is just a string. So you tell this linear layer to be constructed on a CPU or GPU, depending on the string value. Or when constructed, you can put it on a given device by using this to function. So we will not be doing it as a task, but rather I will show you how this code is changed, that the computations are put on the GPU. Okay, so first we have a look if the CUDA is available for our computations, and we already know that it is. So at that point, this device will be equal to CUDA, and then what we do, when we init our MLP, we tell it on which device it should be on, and when constructing those layers, we just put every layers on a correct device, on the same device. Observe that ReLU does not need to be on any device because it is just a function with no parameters, and these are the parameters which are kept on a given device. So for a linear layer, there would be this matrix that is stored on GPU or a CPU. Not a layer, but a matrix with the tensor is stored on GPU or CPU, and the ReLU is just a function. It doesn't have any parameters, so it does not have to be put anywhere. The same for dropout. It is just a function. so we do not put it anywhere. And then when we create our instance of MLP, we tell it to be constructed on this device. So we put it on the GPU. And then when we take our data as inputs, before they got fed into the network, so they are pushed through the network. So before they go to the network, they are put into the same device, just so the network and the data is on the same device. It is important. Sometimes you get an error that the data and the network is not on the same device. Actually, I think I could show you that. If we just skip this thing here, we would get an error. Expected all tensors to be on the same device, but found at least two devices, CUDA and CPU. So the problem here is that the inputs were not put to device, which is CUDA, before they are fed to the forward function of the network. And now it will work. Yes, and look how fast it works. I want to show you how it works. Maybe I run it again. Sorry, I'll just stop it and rerun it. Just so can you see it? It's much faster than the CPU version. Okay, so we have the inputs on the device. The outputs would be on the same device. So before we compute the loss, we need to put the labels to the same device because they are batched, they are a tensor. So the output and the net and the labels, the ground truth labels, need to be on the same device. So before we go to the loss, we need to put the labels to the same device too. Then we calculate the loss, and then nothing happens more. So the only three changes to the code were here, here, and here. Okay, the only three changes. Plus, we constructed our network on the correct device by making sure that each layer goes to a correct device in a constructor. Okay, so it worked much faster than the CPU version. And what about testing? For the testing, observe that again, our network is in the device, so the data point, the input needs to go to the same device before it is fed to the network. Then y hat would be a tensor on a GPU. But here we compare only the items. The item is a function that serves. Remember that the batches for the test set were set to 1, so we get only one item, only one number, which is maybe wrapped in a tensor, but we remove it from this tensor by using this item. So even though this y hat is on the GPU, that item that is removed from y hat is on the CPU already because it is just a number, not a tensor. So then for the calculation of that sum of squares, we just subtract them and square them, and that's it. We do not have to put the labels on the same device because this calculation happens on CPU already. Again, this is on a GPU, but when we take item out of y hat, it gets back to CPU. And look that it will be faster too. We get some higher mean square error, but that's it. And there is another task for you. I will not be going through it. It is to change, but I encourage you to do it. It is to change this sequential, to remove this sequential actually, and to apply all those layers as they are written here in a forward, to define those layers just as we define a dropout, and to apply going through that network in a forward function. So you need to put that X through the first linear layer, then to apply ReLU to the X, then put x through the next linear layer, and so on. And this is the task number 9, which we will not go through because we are already past time. But again, I encourage you to do it in your free time as an interesting exercise. And that's it for today from me, but I will be happy to answer any questions that you might have to what the dropout does. So the dropout, it zeroes out some values because the dropout, as observed before, is sometimes in between layers. So a value before a dropout would be a result of a layer just before a dropout would be a bunch of non-zero numbers, because to get a number equal to 0 is not very probable, as you know, because all those probabilities there are involved, they are continuous probabilities. So we would get from a layer before a dropout, we would get a number of non-zero values, and then we apply a dropout, and with a probability specified when we define a dropout layer. Let's have a look at this definition, for instance, here. So this dropout is the dropout with probability of 1 divided by 100. So with this probability, some of those values would be changed to 0. So the dropout basically does not change 99, this dropout that is specified with this probability of 1 divided by 100, 1%. It does not change it doesn't change the values of 99 values in the tensor that was entering the dropout, but for 1% of them, they are not so fortunate, and they are changed to exactly 0. Okay, and this is used as a regulator, because sometimes we create neural networks that have very many parameters, and too many parameters for them to train effectively. They simply overtrain. This is the danger when having a neural network with which is able to express too much, that it can overtrain. It can just like a student who is preparing for an exam, he's learning he's just remembering all the let's say all the math problems with their exact solutions, but to the letter, like a math problem is specified with at some points with some you know what I mean, and the student that can remember a lot would learn to solve those problems to the letter, but he would overtrain because he would be unable to solve a problem that is different from the one that he has learned. Let's say the point, let's say he's able to solve an equation x squared plus x plus 1 equals 0, but he's unable to solve an equation because he has learned it to memory, but he's unable to learn to solve x squared plus 2x plus 1 equals 0 because he does not know the general method. And this is a problem with neural networks that can express too much, that they learn the training samples exactly, but are unable to generalize. So you provide a test sample that is different from the trained sample, and this neural network gives you a wild guess, which is nonsense. And we regularize neural networks, for instance, by using dropout. There are other methods, and this is largely out of scope of today's talk, but basically this is what dropout does. It makes sure that the number of effective parameters is smaller than the network seems to have. And obviously in evaluation, a dropout cannot zero out anything because we would get wrong predictions. So this is why dropout behaves differently in training and differently in evaluation. Another question. Somebody is writing a question. But then it means that applying dropout twice in a row. Oh yes, it makes it makes and it makes not. So applying dropout twice makes an effective dropout of the probabilities multiplied, or maybe you need to multiply the 1 minus probability. So you know what I mean. So if you apply a dropout, dropping out 10% of the data twice, you probably would to calculate the effective dropout, you would need to multiply 0.9 times 0.9. You would get 0.81. So it means that the effective dropout of applying 2 dropouts with 10% in a row is a dropout of 19%, not 20, not 1%, but 19, because I multiply 1 minus p. I just showed it applying the dropout, applying it twice, just for the purpose of showing how to write the forward pass, not to make an advice of doing it like that. I just wanted to show you how you can write a forward pass, and the data, it goes through the next layer and the next and the next, and it is even called the same, because this is the usual manner that you do that. And you will see it in many GitHub repositories that people do it like that. No. It drops 1%, not of smallest numbers, but 1% of any numbers. So it leaves 99% of numbers intact, and some 1% of the numbers chosen randomly is zeroed out. So if you apply it twice, you might zero out some numbers that survived the first dropout. This is my way of thinking. Okay, so if there are no more questions, thank you very much for staying with me a little bit longer than expected. However, it should be probably expected that it will take longer. Maybe I should change this timing for the next session. Be invited for the, not only for the, there is another message, so maybe it's a question. Maybe I'll just finish what I want to say. Be invited not only for the next day of the workshop, which is in a week, but we do those workshops like once or twice in a year, and usually 2, maybe sometimes 3 of them have the same main theme. Like now we are working with pins, and in a week we will be working with pins. But also this theme changes. So be invited for the next session. I mean, not in a week, but in, let's say, in a year. And I hope it was useful for you. Thank you very much, and thank you for such a kind response, Priyanka Mishra. It is very, very nice to hear that. Thank you very much. Take care and have a great weekend. Bye bye.